So the goal is for you to be able to do those without a calculator in case you saw something like that on the non-calculator portion of the SAT. But knowing what you know about multiplicity, and yay for you, it's already in factored form, do a quick sketch of those three graphs. It has even multiplicity at 3, so what do I expect to see there? A bounce. And again, because of the end behavior, I expect this one to go down and this one to come up. I do expect a bounce here, so this one just comes just like that. There's my quick sketch of the graph. It's not perfect. I didn't even look for the y-intercept. I probably should have, but it's good for a quick sketch. All right. If you have a polynomial function, okay, and it's written in as an inequality, then you have one of these things. Either the polynomial is supposed to be less than or equal to 0, or strictly less than 0, or greater than 0, or greater than or equal to 0. It's not like the inequalities we graphed when we were doing linear inequalities and we did all the shading and all of that stuff. When we're graphing polynomial inequalities, we want to know where the graph is exclusively above or below the x-axis, or sometimes above including the zeros or below including the zeros if it has equality. Okay? And so they're looking for intervals on the domain where the output, right, that's why you guys said, oh, the 0, Mr. Bird, that means the height is 0. Where the output has a positive height or a negative height, and sometimes they include 0 in there. So that's what we're answering. Our answer is not going to be graphing and shading. Our answer is going to be over these intervals, the graph is greater than 0. It's above the x-axis. Or over these intervals, the graph is less than 0. It's below the x-axis. So when compared to 0, this would mean this would be on or above the x-axis is what they want the interval to include. Here would be strictly above the x-axis. This would be strictly below the x-axis. and this one would be on or below the x-axis. So that's what those inequalities mean. They want to know for what intervals of the domain do we have the height either above or below the x-axis. So our first example, we're supposed to do technically a sign chart for this. I'm just going to talk about it with respect to the graphs that we have above for this problem. Then we'll go through the steps and do the formal steps on our other problems. So this is the exact same polynomial function that you have written up here, but this time it says, when is it greater than 0? So when is it greater than 0? I had a highlighter. What the heck did I do with it? Oh, right there. So right here, not including that 0, but everything above that is greater than 0. That green point and that green point are zeros. So they're not above 0, they are zeros. And then everything else is below it. So from here up. So from 3, but not including 3, and then any number to the right would be the domain values that when you plug into the function would give you an output above the x-axis. So from 3, but not including 3, to infinity would be the domain. And that what they're asking here is, where is this function is above the x-axis over that interval. It's above the x-axis over this interval. Now you don't need to write that every time. I'm just explaining that that's what our answer represents. That's what our answer is representing. So for the next problem, they have, again, the same polynomial function we have up here, but rather than it being equal to 0, where we're finding the zeros and sketching the function, we're now saying, when is it less than, strictly less than 0? So we're asking where or over which intervals is it below the x-axis? So we look at our graph and we say, oh, you want to know where it's below? Well, here it's exactly 0, and I don't want the 0, so I'm going to put an open circle. Here it's exactly 0, so I don't want 0, there's an open circle. Here it's exactly 0. Here is where it's below, and over here is where it's below. So I'm going to have a couple intervals. I'm going to have an interval for every number to the left of -1, so that's negative infinity up to, but not including -1. Negative infinity up to, but not including -1, joined with one more set of parts, another part of the graph that's below the x-axis, and that's from 0, but not including 0, all the way up until I get to 4, but again, not including 4, because 4 is equal to 0. So from 0 up to 4. Any questions on that one? All right, and then on our last one, again, this is the same function that you have graphed above when you solved and found the zeros and then did a sketch of the function. And they're asking, when is it less than or equal to 0? So they're asking, when is it on the x-axis, on or below the x-axis? And so it's on the x-axis right here at the zeros, so I need to color those in because those actually are 0. And then everything over here, down from there. So it's not the same equation? I meant for it to be. Let's make this a +5, sorry. All right. So in this case, then I include those zeros. So it is from negative infinity up to negative, up to -5 and including -5. So from negative infinity up to -5 and including -5, because that is a 0. And if it's equal to 0, it would make the inequality true. Yeah. Oh, yeah, what am I doing? Thank you. Negative infinity always has a parenthesis. Thank you. So focused on this, I wasn't paying attention. All right. And then the other one is this 0 over here at 3. So it's just here. I got ahead of myself with the brackets. The brackets go around the 3. Yep. Any questions on that? So that's just by looking at the graphs, but there's a little bit more to it. We're supposed to show our evidence using a sign, what's called a sign chart. So we're going to be looking at those. The steps to solving a polynomial inequality is to set the inequality equal to 0. Because sometimes I have an equation on one side and an equation on the other. That's not easy to solve, okay? But if I move everything to one side, then I'm comparing everything to 0. Then I'm thinking about it as, with respect to the x-axis. When is it above that line? When is it below it? Okay. So think about this. If this had been a 10 over here, then I would have subtracted 10. It would have shifted everything down 10 units. So with that idea in mind, we want to make our baseline when we're comparing our inequalities. We want to make the baseline 0. So we're comparing it to the x-axis. We're going to find the domain, which for polynomial functions are pretty easy. We will have to do that when we do rational functions and radical functions, and we'll be looking at those tomorrow. And simplify if necessary. And then find the zeros of the polynomial by any and all means. What they mean by that is hopefully by factoring, which is either factoring or solving. Maybe you have to use the quadratic formula if you've gotten it down to a quadratic. Or graphing. If you can get them from graphing, go for it. Okay, you got your zeros. You have a way of showing that those are your zeros. Make your sign chart using those numbers. It's not always going to work out conveniently by graphing, though. You may have to use rational roots theorem and or breaking that polynomial down to solve the quadratic formula. Plot the zeros on the number line, which I call the sign chart. I don't even make mine a number line. I just put them in correct order, like lowest to highest from left to right. And then test points to see if the graph is above or below the x-axis. Again, that's going to be part of what we call a sign chart. So we're going to go to the next page to go through these steps as we solve a couple of these. Oh yeah, they're there. All right. Solve the inequality for x. Well, in this case, we need to get it equal to 0 or greater than or equal to 0. So I'm going to subtract 1 from both sides. This gives me my new polynomial function, which is equivalent in terms of my answers for x for this will be the same answers that would be for x for this. So this is going to give me x squared minus 8x plus 15 is greater than 0. This inequality and this inequality are equal in the sense that they represent the same values for x, because all I did was subtract 1 from both sides. So now instead of comparing this inequality to a baseline of y equals 1, where does the graph fall above y equals 1? Right? If you think about these, this is a polynomial function and this is the function, the horizontal line y equals 1. I have to compare it to that. I'm comparing it to the x-axis, comparing it to where y equals 0. So now I'm going to find the zeros. I'm going to do this by factoring if it's factorable. If not, use the quadratic formula or look at my graphing calculator, although I won't be able to see it if it's not factorable. All right, so this will be x minus 5 by x minus 3. That adds to negative 8, multiplies to 15. This gives us zeros, which is where f of x equals 0 at x equals 5 and x equals 3. So if they said, when is the function 0? Well, that's the answer, at 5 and 3. That's not what they're asking. They're asking, when is it strictly greater than 0? So I'm going to make what's called a sign chart, and this is part of the showing the work for this. My sign chart will have my zeros, kind of like on the number line. There's my 5, there's my 3. And it will have plus or minus signs to each side of those tick marks. Okay, here's my 3, here's my 5. I'll have either a plus or minus sign here, a plus or minus sign here, a plus or minus sign here. So it's not an actual graph, it's just representing what happens, what the function is doing. I already kind of expect to know what's happening because I see that this is what type of function is this? Quadratic with a positive lead coefficient, which we're going to be talking about in a second. So you kind of know the shape and what you expect it to look like anyhow. But I'm going to put in my graphing calculator, and I'm going to do the sign chart using the table, but I also could even do it by looking at the actual graph itself. So x squared minus 8x, I'm going to put in this function, the one that I'm comparing to 0, plus 15. And I'm going to, if I put in 3 and 5, I get 0. That's great. But I need to plug in a number to the left of 3, so I'm going to test 2 to get my sign there. I'm going to test 4 to get my sign there, and I'm going to test 6 to get my sign for that value. So in my calculator, I'm going to plug in 2, 3, 4, 5, 6. And I can see that to the left of 3, I have a height that's positive. So I put a plus sign to the left of 3. And I can see that between 3 and 5, which were my zeros, I have a negative output for when I put in 4. So that means that that's where it falls below the x-axis. And to the right of 5, which is what I get when I plug in 6, I get a positive answer. So what this means, the plus signs mean that to the left of 3 and to the right of 5, the graph falls above the x-axis. And in between 3 and 5, the graph falls below the x-axis. That's what my sign chart is showing. The plus indicates above the x-axis. The minus indicates below the x-axis. Now that's not my actual answer. That's just part of the evidence that I'm showing that I made a sign chart to figure it out. And honestly, I could look at the graph. I should see the same thing. To the left of 3 and to the right of 5, the graph is going above the x-axis. And between the two of you, it's just dipping a little bit below. And so my answer is the intervals of the domain for which it does this. And I want the intervals where it's greater than the x-axis, above the x-axis. So that's going to be to the left of 3. So negative infinity up to but not including 3 because it didn't have an equal sign. I don't want to include the 0. I had some students who even will put an open circle there because they know that it doesn't have equality. They don't want to include the 0. It's a visual way for them to see that it's not going to include those. And then it's also positive or above the x-axis for anything to the right of 5, but not including 5 because 5 is a 0. So again, if you have greater than or less than, then you should be using brackets for your numbers. Okay? If you have strictly less than or strictly greater than, then you should be using parentheses for your numbers. But sometimes this can help to put the open circle or a closed dot at the 0 to help you remember to include it. Any questions so far? By the way, I want to show you how this compares. So here's what I'm looking at. I have this function and I have y equals 0. I got two functions here. Let me change my window. You don't need to do this. But I can see right there, I'm going to look for, and y equals 0 is just there. I can trace the intersection of those two graphs if I wanted to. There's going to be 2. There's one of the solutions, 3, 0. And I could do the same thing, find the other intersection point. But what they're saying is, hey, where is it above 0? Now the same thing is true if I had compared this. X squared minus 8x. You don't have to do this. I'm just showing you why this works. Plus 16 versus y equals 1. Oh, shoot. I don't want 3 functions. I want 2 functions. So if I look at this graph, now I'm saying where is this graph above where y equals 1? Above those intersection points is here and here. Again, it turns out to be the same domain, where x is 3 is where they intersect, where x is 5 is where they intersect. So let me show you that. The intersection of curve 1, where's curve 1? Oh, there's curve 1, and curve 2 gives me one of them there at 3, 1. So again, it's still the domain. 3, everything to the left of 3, everything to the right of 5. So we're just going to set it equal to 0 and work off of that, though. So for our next function, we're going to subtract 46 from both sides, giving us the equation or inequality x squared minus 9x minus 36 is less than 0. In solving this inequality, it'll be the same answers for x. That would be a solution to this inequality, because all we did was subtract 46 from both sides. So we're going to factor that if it's factorable. I think it is. Is it 12 and 3? X minus 12, x plus 3. And so the zeros are x equals 12 and x equals negative 3. And so on my sign chart, and it's supposed to be an underline, I'm not that picky as long as you have it correct from left to right. Negative 3 is going to be somewhere over here, and 12 is going to be somewhere over here. I need to have, because I have 2 zeros, I need to have 3 signs. A sign here, a sign between them, and a sign to the right. And so I'm going to plug this function in. And I already know the behavior of this function, but we'll talk about that again in a second. So this is x squared minus 9x minus 36. And I go to my table and I plug in a number to the left of this. For me, I'm choosing negative 4. Between negative 3 and 12, I'm going to pick 0. And to the right of 12, I'm going to pick 13. And sure enough, to the left, I get a positive number. So I put a plus sign on my sign chart. And a negative number between the negative 3 and 12. And a positive number to the right of 12. Any questions on how to make your sign chart? So that's part of our evidence right there is our sign chart. So now they're asking when is, well, they asked when is that function less than 46. That's the same as when is this function less than 0. Well, so I don't want to include the zeros as part of the intervals. It's between negative 3 and 12 that it dips below 0 or below the x-axis. So my interval for this solution to this inequality, which will solve this inequality, is negative 3 to 12. And if I look on the graph, I should see between negative 3, well, my graph doesn't show 12. I have to change the window. Between negative 3 and positive 12, the graph dips below the x-axis. So I can check it with the graphing calculator. Questions on that? Now I'm going to warn you to be careful because our examples that we have right here have alternating signs. And a lot of times they do have alternating signs. When are the signs not going to alternate anymore? Think about types of functions and what we looked at in the beginning. Maybe even look at the first page. Take a look at the first page, those graphs that you did at the beginning of class. When are the signs not going to alternate? Would that happen for any of these graphs here where it wouldn't be like plus, minus, plus, minus, plus, minus? I can tell you it's going to happen for at least 2 of the graphs on the first page. When? When it bounces. And when does it bounce? When it has even multiplicity. If it has odd multiplicity, it just does a twist, but it still changes from minus to plus. But if it bounces, it maintains that sign. To the left of this 0 and to the right of this 0, we're below the x-axis. To the left of this 0 and to the right of this 0, we're above the x-axis. So you can't just assume that your signs are always going to alternate, because if there's an even multiplicity, they won't. So you need to know whether or not there's even multiplicity or not if you're just going to start filling in signs without testing points. I always tell students it's best to just check a number between and to the right and left of all your zeros rather than to just assume they're going to alternate, because if you have multiplicity, it's going to throw it off. So in this next thing, this is why I don't really care for this. It says solve the polynomial inequality using n behavior. So you're looking at this going, oh, that's a cubic function. Okay, I can do that. I know how a cubic function behaves. It has a lead coefficient. So I'm expecting the n's to do this, just like they did on the front page, which is great. Now you know that to the left of the leftmost zero, it's going to be negative. To the right of the rightmost zero, it's going to be positive. But you can't be positive that it's going to alternate unless you know some more about the function. So we've got x cubed minus 3x squared minus 22x plus 24, because I'm subtracting 3x squared and adding 24 to both sides, so that I can solve this inequality instead and compare everything to the x-axis. This, unfortunately, is not factorable. Now, we probably could use rational roots theorem and divide something out and solve for all the zeros that way. But how else could I get my zeros? Anybody know? Nobody remembers. I could trace it. I could also do the second trace, which lets me calculate them. And as long as they're not irrational, then I could at least approximate. I know for me, I could use rational root theorem too, right? I could use rational root theorem even without dividing out. If they're all rational, then I'm set. If they're not all rational, then I might have some more work to do. So I'm not seeing the whole graph, but I'm seeing some of them. And I can see that it looks like this one's at -4, and this one's at 1, 2, 3, 4, 5, 6, and this one's at 6. So I'm going to go to my table and check. Is -4, 1, are -4, 1, and 6 zeros? They are. So I didn't even use the rational root theorem. I could have done factors of p over factors of q and plugged them in, but I was able to get them right from the graph. So that's fine, as long as I have my sign chart to show my evidence. So those are my zeros. The zeros are x equals -4, x equals 1, and x equals 6. Now, technically, if I'm solving this algebraically, I'm supposed to use the rational root theorem, break it down to a quadratic, factor it, or quadratic formula to get all my zeros. But I just need the zeros for the sign chart, so I'm not worried about that. If this were an equation and I told you to solve it, you would have to show me all that work. So here's going to be my sign chart. I've got -4 on this sign chart, 1 here, and 6 here. And those are not evenly spaced, so it's not really a number line. It's just a sign chart. Technically should be a number line. So in my calculator, because my graph didn't quite show it and I don't feel like playing with the window, I'm going to go to my graph and calculator. I'm going to test a point to the left of -4. I'm going to test, and that ended up being negative. I'm going to test a point between 4 and 1. Let's go with 0. That ended up being positive. I'm going to test a point between 1 and 6, so maybe 5. That ended up being negative. And to the right of 6, we already know what's going to happen because of the n behavior, but we are expecting it to be positive. So for this problem, we expected to the left for it to be negative, to the right of this one it to be positive. Because I have a third 0 here, I didn't have multiplicity. I didn't have to worry about multiplicity. In this case, the signs do alternate. I'm going to tell you, though, just to be safe, I would still test a value on each in case you missed some multiplicity. Not going to be true for this one, though, because it's a cubic and we have 3 distinct zeros. Go ahead and give that a try for this problem, but call this 9x squared. That 2 was actually supposed to be a square. So see if you can find the zeros, make a sign chart, and then answer. Oh, I didn't answer the final problem. Whoops. So they asked, when is it strictly greater than? So it does not include my zeros. Well, that's going to be 2 intervals. From -4 to 1, the graph is above the x-axis, and to the right of 6. So -4 to 1 joined with 6 to infinity. So there's my final answer, and this is the work that supports that answer is my sign chart. Give that a try for the next problem. So for this example, you should get the zeros. You can get them from the graph or from using rational root theorem, plug them in. And we get -4, -1, and 1/2. And so we put those on a sign chart, -4, -1, 1/2. And I have to test everything to the left and right of these zeros, check some points to make sure to see what the signs are. So to the left of -4, I plugged in -5, I get a negative sign. Between -4 and -1, I'll try -3, I get a positive output. Between -1 and 1/2, I'll try 0, I get a negative output. And to the right of 1/2, I'll put 1, I get a positive output. Again, I did expect this, given the lead coefficient is positive and it's an odd degree, that to the left it would be going down and to the right it would be going up. And since I have all 3 zeros, it's okay for me to just alternate the signs. If I'd only had 2 or just 1 for a cubic or 2, then I would expect some multiplicity and I'd have to look carefully for what happened with the signs. So my intervals for this, I want to know where is it strictly greater than 0. I feel like we were supposed to have some that had equality, whatever. We would have from -4 up to -1, but not including either of those, joined with 1/2 to infinity. Because anything to the right of 1/2, those inputs, those domain values of x will lead to a positive height on the graph. Any questions on that one? All right, so for the last example, it's saying the same thing, except this time we're looking at some that have equality and some that don't, and there's some minor twists to these. This first one is not factorable. If you look carefully, they're the same inequality. I did that on purpose for time's sake, but to exemplify 2 key things. For this one, I cannot solve for x by factoring. This is not factorable. So I turn to the quadratic formula to see if maybe it's irrational. So I've got -2 plus or minus, and this is over 2, this is over 2, because a is 1. B squared, which is 4, minus 4 times a times c, so times 1 times 3 is -8. So I've got the square root of -8, which is really 4 times 2 times -1. So it's 2i square roots of 2. The square root of 4 is 2, square root of -1 is I, square root of 2 is left over. The 2's cancel. I have my answers for x. I don't really care about my answers for x unless they're just irrational. In this case, they're not even real. They're complex. They involve imaginary numbers. So what's that going to look like on my graph? When the discriminant is negative, what does that mean? Well, it means that my answers are not real, but what does that mean in terms of the graph? It never intersects the x-axis, which means it's either above or below. What do you think it's going to be in this case, given the lead coefficient? It's going to be above. And you can sketch in your calculator to see, but yes, my x-axis is here, and the graph is above the x-axis. So what that means is, when they're asking me, when is this function less than 0, well, that's never going to happen, right? So the answer to this one is no solution, because it's never below the x-axis. It doesn't even intersect the x-axis. Now, if that had been less than or equal to, well, then that'd be, oh no, still not equal. It would still be no. It would still be no solution. This one's greater than or equal to 0. Well, it's not equal. There's no points that are equal to 0, but every point is greater than, so this would be all real numbers, which in interval notation we represent -infinity to +infinity. So every point for this function is above a height of 0. That's what this is saying. Every point, all values of x that I could plug in here would give me a height greater than 0, which meets greater than or equal to 0. For my next problem, this one actually is factorable. This is x plus 6 by x plus 6, or x plus 6 squared, which means x equals -6. which means I only have one solution. If I only have one solution for a quadratic, what's it mean about that solution? Multiplicity. And this function, because of the lead coefficient and degree, we know it opens up. So if I were looking at the graph, I'm just going to sketch it. It's not really, I'm going to sketch it because I know it. And I didn't put a sign chart here. Technically, we should have a sign chart. There's -6. That's on the x-axis. That's the only 0. It has multiplicity. So if I were making a sign chart for -6, I'd have positive to the right and positive to the left. So all values other than the 0 are positive. But there is a 0. So right here, less than or equal to 0, well, there aren't any points less than, but what is? What number is going to count? -6 because it equals 0. Since it is a 0, the solution to this is just -6. It's the only value of x that would make that inequality true. It would be 0 equals 0. This would be 0 on the left, and you got 0 on the right, so that would make it true. For this one, they say, for which values is this function greater than 0? Well, this time it's not all real numbers. It's everything except for -6. So it's to the left of -6 and to the right of -6. So -infinity up to but not including 6, or sorry, -6. And -6 to infinity but not including -6. So the goal from this, and again, I usually, when I make my sign chart, plug numbers in to test everything. In this case, I just used what I knew because it was a quadratic. But you can look at the graph. You can use that to make your sign chart. You could have plugged in -7 and -5 to get your sign chart. Once you have your sign chart and you're looking at the inequality, you should be able to write the intervals of the domain. The required assignment for making sure that you qualify for reassessment options are those problems right there. We do have a quiz on 2.5 coming up on Friday and your benchmark test next week. The quiz will only include 2.5, so you might want to do some of those review problems, make sure you're solid on that. Okay? So that's what you guys are going to be working on and getting help with if you have questions.